We're going to take a look at some charts. Do you guys remember the lesson where we did instantaneous rate of change given a chart? You want to look at the numbers before and after? It's more or less the same lesson, okay? So let's get right into it. Just remember, a great example for derivative, a great visual example, a real-world example is a car and a car speed. So here we have a chart. Go ahead and copy this down. Some of the points for a function are given below. That means it's not all the points, right? We have 1, 2, 3, 4, and 5, and then some numbers associated. So the question asks, what is the instantaneous rate of change? And again, that just means derivative. We'll start using that word more, but I'm just going to write that word above it because it means the same thing. What is the derivative or instantaneous range of this function at x equals 3? So again, just like instantaneous rate of change, you can pick points before or after, find the slope between those 2 points, and it will give you an approximation for the derivative at 3, which also, another word for derivative is slope of the tangent line. So all 3 of those mean exactly the same thing. Just talk about it. We don't know. We talked about the speed of a car, and we said that basically, the way your speedometer works is it's only measuring data, before and after. It's measuring the change in distance over change in time in a very small window. The same thing is true for derivative. We can only really use points on the graph before and after. Yesterday we looked at the difference quotient, f of x plus h minus f of x over h. It's the same concept. H becomes really, really small to the point where it's almost 0. But that's what a limit is, right? It's approaching 0, but it never gets there. And so, just like instantaneous rate of change, we're going to choose the 2 points that are closest to 3. Now, I want to talk a little bit about another method that you might see. Someone might choose the actual point itself, 324, and then 4, 40. But the reality is, in order for the difference quotient to work for h, think about this. If h is approaching 0, it's not just approaching it from the right, it's also approaching it from the left, right? If we talk about the limit as x approaches 0, we don't put a plus sign up to the right of the 0. We don't put a minus there either. It's coming from both directions. So h, has to be both positive and negative. And so when we're choosing points to the left and right of our derivative value 3, you need to choose left and right, because what if there were no values over here? If there were no values over here, then the limit for h wouldn't exist because it's only coming from the right. So I think we should use points to the left and right to make sure of that. And that actually comes up in a equation. It's probably not going to make sense to you right now, but f of x equals x to the 3/2. The derivative at 0 doesn't exist, and that's because there is no graph to the left. But anyways, we'll talk about that later. So here's our 2 points. To find the slope of those 2 points, we just use the formula that we're used to, which is y2 minus y1 over x2 minus x1. But for this particular example, we are estimating the derivative. And remember, the derivative of a function, we use f prime. Now c is just some value in general. In this case, c is going to be 3 because we're figuring out the derivative at 3. But this is the general formula. So basically what we're saying is the slope of the secant line around this value is approximately equal to the derivative at that value. If we were to look at a graph of, let's just draw like an x squared graph or something. Okay, and let's say that we were trying to figure out the slope of the tangent line right here. Not perfect, but close enough. So actually what we're really doing is we're finding the slope of a secant line that's close to that. Can you see that basically those slopes are almost the same? That's what we're doing when we're finding points before and after. We're finding a slope of a line that should be pretty close to the slope of that tangent line, just like that. Now, it doesn't always work out that way. Sometimes, you have to get really, really close before these slopes, become the same. So now we're just going to find the slope, y2 minus y1 over x2 minus x1. So it's 40 minus 18 over 4 minus 2. And again, we're finding the derivative at 3, or approximating it. So we get 22 over 2, which is 11. So what does that actually mean? That actually means that given this chart, the instantaneous rate of change at 3 is approximately 11. If we were going back to the car example, let's say this is how many meters it's traveled after so many seconds. So after 1 second, it went 12 meters, 2 it went 18, 3 it went 24. We are guesstimating that at 3 seconds, it's traveling 11 meters per second, the slope of the tangent line. Okay, so let's go ahead and do this chart. This one won't take long. You've already written the steps out, so you can basically just write the solution for this one. Here we have some decimals for x value, and we have negative numbers for y. It says, what's the slope of the tangent line at x equals 22.10? So now we're going to be focusing on these values. So we should be using this point to the left and this point to the right. I'll give you a second to copy that. Actually, the chart's on the next page, so you can copy it there. Okay, so we're going to be using the point to the left, 22 comma negative 7.7, and point to the right, 22.11 comma negative 7.9. One thing I want you to notice is what's happening to the y values as the x values increase. They're going down, yeah. So that's an indication that the slope is going to be negative. The slope of the tangent line is going to be negative. It's like if you were, backing your car up, your velocity would be negative. So your position relative to where you started would be negative. If it's going down, then your velocity is also going down. Okay, so, same thing. You can just write y2 minus y1 over x2 minus x1. It's the same concept. We just like to use f because, function notation. So it'll be this minus this over this minus this. And the reason I did a negative is because when you subtract a negative, it becomes positive, okay? So in reality, it's minus negative 7.7 on top. Okay, the bottom is just 22.11 minus 22. So what is negative 7.9 minus negative 7.7? Anybody know? Negative 7.9 minus negative 7.7. Nope. It's going to be negative 0.2, okay, because it's like negative 7.9 plus 7.7, so you don't quite get back to 0. Negative 0.2. And what I did, the trick I did here was if you move, let's see, that is not right. You'd have to move the decimal over twice here. Let me double check. Yeah, so actually there'd be a 0 right here. Negative 20 over 11. I'm glad I caught that. So the slope of the tangent line would be approximately negative 20.11, which actually, is basically negative 2. Okay, not exactly right. If it was negative 20 over 10, it would be negative 2. But it's a little bit less than that. Negative 20 over 11. So if we were looking at the slope of the tangent line for this chart, it would look something like this. Okay, you'd be going down 2 and over 1. All right, we're going to do one more example. And for this particular example, you're going to see that sometimes you have to resort to a different method. This is asking what the slope of the tangent line is at x equals 0. Now, if we look on the chart, there's no point to the right. There's only points to the left. So when that happens, you have to end up using the point itself plus the point to the left because you have to have 2 points. In the same way, if you were only given like the first point and nothing to the left, then you would use that point and the point to the right of that. So you can only use the 2 points around it when that actually exists. So for this one, we're going to use the point itself at 0, where we're trying to find the derivative, plus the point to the left. So it'll be negative 0.001, comma 0.005, and then 0, 0. Okay. So the top we're going to have 0 minus that, so it's going to become plus that. Okay. The bottom is going to actually be negative. It's kind of weird, but it'd be 0 minus. The reason that is because these numbers are actually decreasing. I'm sorry, numerator. This is the numerator. I'm getting confused here. The denominator will be positive. The x values are increasing. The y values are decreasing. So it will be the same formula. So on the top we'll have 0 minus 0.005 because the values are going down, and then 0 minus negative 0.001, like that. So that's y2 minus y1 over x2 minus x1. So it becomes negative 0.005 divided by 0.001. And since they're in the same place value, okay, we can certainly just kind of ignore the zeros and write it as negative 5 over 1, which is just negative 5. And again, if we were looking at the graph, it would have a slope of negative 5, so it would be pretty steep going down from left to right. It would go down 5 and 1 to the right. And that'd be the slope of the tangent line. So it'll only be at a single point. So your graph might be, look something like that, where it would be very steep. I don't know, just an example. That's it for this. I'm not going to give you an assignment on this because we've already done one very similar. But tomorrow we're going to learn the power rule, and it's very simple. You'll like it.